All right, I think we are officially live and broadcasting. It's 4:15. This is our Che Calculus office hour. We're going to get started here in just a moment. We're going to give everybody just a few seconds to kind of start coming in and join us as we get ready to review and talk about answering your questions that come from calculus. And I'm just going to push a little button here so that everything is live and active on the feed. And hopefully people will be able to join us. So just want to start off with a big hello to everybody who's rolling in. This is our live office hours for calculus, brought to you by Che. I'm Wallace STEM. You probably know me from my accounts at Wallace STEM on TikTok, Instagram, Twitch, YouTube, and the like. Hopefully you're following me there. I like to take memes, trending sounds, and make them about math. So I say, come for the memes, stay for the math. It's a lot of fun. And here today, we're partnering with Che to offer a live office hour focused on calculus. So for those of you that have been here before, welcome back. We're excited to have you here. But for those of you that are here for the first time, the goal today is to help you understand your calculus course and concepts better. And I am here every week at this time. So mark your calendars, 4:15 Pacific time, 7:15 Eastern time. We're going to be here answering your calculus questions. So come with questions. Come with homework problems, come with your notes, and get ready to have a lot of fun talking about calculus. This is your office hour, so drop your questions in the chat, and I'll do my best to answer as many of your questions from the chat as possible as the hour goes on. Last time I was broadcasting live, there were lots of questions specifically about trigonometric substitution. Probably because it combines algebra, trig, and calculus into one problem, and that can create a lot of questions. So we're going to start with some trig substitution, then we'll dive into some of your questions, which might include, like I see the one who waits wants to talk about some differential equations. We can hit those right after this example. We're going to start with some trig substitution. Let's do the integral of 1 over x squared, square root of x squared plus 4 dx. Now with trig substitution, the idea is we want to make a substitution that's going to allow us to use a trig Pythagorean identity to get rid of this square root. And to do that, we're going to let our x's equal. If we're adding the two terms, we're going to make it a tangent. I'll take the square root of 4, which is 2, and we'll make it a tangent of theta because the property with tangent is that tangent squared plus 1 equals secant squared. That makes our dx equal to 2 secant squared theta d theta. So we're going to substitute that into our equation and see what we end up with. We have the integral of 1 over x squared, which is 2 squared tangent squared, or 4 tangent squared theta, times the square root of x squared, which again is 4 tangent squared theta plus 4, dx, and dx we said was 2 secant squared theta d theta. And it looks initially like we've made the problem more complicated. But the truth is we've actually made the problem simpler because inside this square root, I can factor out a 4, still under the square root, and that'll leave me with tangent squared theta plus 1. But tangent squared theta plus 1 is just secant squared of theta. And now we can take the square root of this expression. The square root of 4 is 2, and the square root of secant squared is just secant. So now I can go back in and do some reducing. I can reduce out this 2 with that 2. I can reduce out this secant with one of these secants. And so what we end up with is the integral of secant theta over, well, let's pull the 1/4 all the way out, tangent squared theta d theta, which is a much nicer, simpler integral to work with. And I think we can even do some convenient factoring and reducing on it because secant theta is 1 over the cosine of theta. And tangent theta is sine squared over cosine squared of theta. And so when we multiply by the reciprocal on this guy, puts the cosine squared on top, one cosine is going to reduce with one of the cosines. So I now have 1/4 of a cosine theta over sine squared of theta d theta. Multiplying this cosine on top, this sine squared is on the bottom after reducing. And this integral is really easy to solve using a u substitution. So let's do that. Let's make u equal to the sine of theta, which means du is equal to the cosine of theta d theta. If that's the case, we now have 1/4 of the integral. Cosine theta d theta all becomes my du. Sine squared becomes u. In the denominator means we've got u to the -2. And this is an integral that we actually know how to solve and get our answer. I'm going to come over here, and we've got 1/4. We're going to increase the exponent by 1, making it u to the -1. Divide by the new exponent, making it negative. And we've got the plus c. And now that we've integrated it, we just need to go back to ultimately to our x's. But we got there first by going through u. So u is going to be the sine of theta. So I've got -1/4 times u to the -1 is 1 over u, which means we have 1 over sine. And 1 over sine is cosecant of theta plus c. Now that we're back to thetas, we're going to use our original substitution to draw a triangle to get rid of the thetas. From this theta, we said tangent is, if I divide both sides by 2, tangent is x divided by 2. Tangent is opposite over adjacent. So x is the opposite. The adjacent is the 2, which means the hypotenuse, using the Pythagorean theorem, is x squared plus 4. Our answer, though, is going to be -1/4 times the cosecant. Well, cosecant, the reciprocal of sine, is hypotenuse over opposite. So it's -1/4 times the square root of x squared plus 4 divided by the adjacent, which is x. And of course, we're going to have a plus c. Might want to clean that up. This last step's probably optional, but if 1 times the square root is just the square root of x squared plus 4 over the 4x plus c, we have finished our integral. So that's trig substitution. Some of these problems get a little bit longer, but no step along the way was really challenging or new. The whole thing was based on this idea that tangent squared plus 1 is secant squared to allow us to simplify the radical. So x is tangent with the square root of the 4. Make the substitution and do some trig simplifying, and that'll give us an integral that hopefully is much easier to handle. And in this case, it certainly was with a quick u substitution. So for those of you that are just rolling in, welcome. This is Chake's Calculus Office Hour to answer your calculus question. We just took a look at trig substitution because last time I was live, there were a lot of trig substitution questions. But I want to know what questions you're working on right now in your calculus class. Remember, we're here every Thursday at 4:15 Pacific time, 8:15 Eastern time to answer your questions. So mark your calendars. Come next week, come this week. We're going to answer all of your questions. There are lots of questions coming in. One question came in that wanted to talk about differential equations. Now, different calculus classes go different depths into differential equations. I know you wanted to talk about Laplace transforms. That's probably a little bit advanced for like a calculus class, but we can do a separable differential equation. So let's take a look at a separable differential equation. That's going to be something like x e to the -t dx dt is equal to t. These are the type of differential equations that you might see on the AP Calculus exam. On the AP Calculus exam, most of the differential equations you're going to see are what are called separable differential equations. The idea is we can get all of one variable on one side, all of another variable on another side, and just integrate to get it out of there. So since dt is in the denominator, we're going to multiply both sides by dt, which means I need everything with t over here on the right side. This is e to the -t. I'm going to multiply by e to the t on both sides so that e to the -t and t can reduce out. Then I'll also multiply by the dt on both sides. And that's going to just give me x dx is equal to t e to the t dt. And now we've separated the x's on one side, the t's on the other side, which means now we're ready to actually go in there and integrate both sides of this equation to find our solution for x and t. On the left side, that's a really easy integral. That's x squared times 1/2. Let's go ahead and put the plus c on that side. It doesn't really matter which side gets the plus c, but we need to make sure we remember the constant. On the right side, we're going to do this with integration by parts. We're going to, just looking over to the side here, integrating t e to the t dt. If u is equal to the t, du is equal to dt. That means our dv, the rest of the expression, is e to the t dt. And the antiderivative of e to the t is just e to the t. So when we integrate this, we do u times v, which is t e to the t. Then we do minus the integral of v du, which is e to the t dt. And this antiderivative, the antiderivative of e to the t is just e to the t. So this total integral comes out to be t e to the t minus e to the t. And that's going to be our final solution. If you're on the AP Calculus test, I would highly recommend you stop here. This is a safe stop. Remember, the AP Calculus test does not give you extra points for simplifying or doing the algebra. But if you do the simplifying and make a mistake, it will dock you points. So as soon as you have a safe stop, you've got the derivative or the antiderivative taken, stop. Don't do any more simplifying. So that's differential equations. Thank you for that question. I'm looking through the other questions that are coming in. We've already got some great questions coming in. Keep your questions coming in. Remember, this is your office hour. I want to explain the different types of different powers of infinity. That is a deep and long rabbit hole to go into. I'd love to, but probably not time for this. Drew wants to look at delta and epsilon proofs, though. Those are really important to calculus. They're predictable in that they follow the same pattern every time, but kind of learning that pattern and understanding what's happening can be really tricky. So the whole idea of the delta epsilon proofs is we say that the limit as x approaches something of f of x is equal to L. What that means, oops, I'm on top of the QR code. By the way, scan this QR code in the corner. Great thing to scan so that you have I'm going to mark the QR code so I don't write on top of it again. Scan that QR code so you have the live schedule so you know when we're live with various subjects throughout the week. Chegg is live all the time with some great tutors. Check them out. But anyways, I was saying that the limit as x approaches a of f of x is equal to some L. This is defined if and only if for all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of x minus a, oops, actually I should have a 0 in here, such that 0 less than the absolute value of x minus a is less than delta, would imply that the absolute value of f of x minus L is less than epsilon. What the heck does that mean? I hear you cry. It is a terrible, ugly looking thing. It's kind of a fun party trick to spit that out because there's like no numbers in there and it looks pretty cool. It makes you feel pretty smart. But really, all it's saying is the different parts and pieces of a delta epsilon proof. Let's say we want to use this to prove that the limit as x goes to 2 of 3x minus 5 is equal to 1. Well, the way we prove that is, so this is what we're trying to prove, that the limit is equal to 1. We say for all epsilon greater than 0. So we're going to say let epsilon be greater than 0. That's this first part. Then it says that there exists a delta. So if there exists some delta, that means I can choose. Does choose have 2 O's or 1 O? This is a math live session. It is not an English session. I promise nothing about my spelling or my artistic capabilities. But choose, I think, has 2 O's. Let me know if I'm wrong. Whoops. Something just weird happened on my page. I'm getting an error message that says something went wrong. Try reloading the page, and I lost the entire chat. So I don't know if I'm still live. Hopefully you can all still see me. I'm not sure what that error was. Let's finish this proof. I'm still live. Everything's still working. Okay, so I don't have the chat anymore, but we're bringing that back. I'm being told they're working on reloading it for me. They might have to send me questions through the private chat. We'll see. All right, we're going to choose a delta because we're saying there exists a delta. We can choose that delta to equal whatever we want. We're going to hold on that. We're going to choose it to be equal to whatever's convenient to us in just a minute. In the meantime, we're going to assume this piece, that the absolute value of x minus what it's approaching, the 2, is actually less than this delta, whatever delta we're going to pick that's going to be convenient in a minute. All right, now comes the fun. We're going to figure out what this is, and we're going to show it's ultimately less than epsilon. The function is this 3x minus 5. Then we're going to subtract the limit, which is 1. And we're going to do some work with this to hopefully show that it's less than epsilon. So whatever we do here is going to end up being less than something that gives us an epsilon. That's what we're trying to show. Well, the absolute value of 3x minus 5 minus 1 is the absolute value of 3x minus 6. And if I factor a 3 out of there, I get the absolute value of x minus 2. This x minus 2 should look familiar. This is what we assumed was true just a second ago. So I can replace this with something bigger than it. I'm going to replace it with delta. So the 3 is still there, but the something bigger than it is delta. So we want delta to be something so that when it's multiplied by 3, the answer is epsilon. So we're going to make delta equal, because I can choose it to be whatever I want. Delta is going to be epsilon over 3. So that when I replace delta with what it represents, epsilon over 3, boy, that's funny because they look like they're mirror images, the 3's reduce out, and I end up equal to epsilon. So that's how I kind of work through the definition of a limit, doing an epsilon delta proof to show that ultimately 3x minus 5 minus 1 is less than epsilon. Excellent. Great work. Okay, so great question. I do not have a chat right now, so I don't see any messages coming in. Hopefully, we can get that tech figured out. But go ahead. I'm told that the chat messages are still coming in to the Chegg people, and so the Chegg people can try logging in there. I'm going to try refreshing my page, actually. Let's see what happens when I click the refresh button. Hopefully, we don't. The chat. Hey, we're all back. We're live. Everything's working. Excellent. I love technology. Sometimes we just have to kind of go with the flow, and that's the fun of live. But hopefully everything is going well. Thank you all for your patience in staying with us. I'm trying to get caught up on the chat because there's been a lot of great comments coming in. We just did Drew's delta epsilon proofs. The integral of the cosecant theta, cotangent theta. Sure, let's take a look at that from user 310 on TikTok. You're giving me a problem. While I'm erasing, remember this is your office hour. We're here every week at 4:15 Pacific time, 7:15 Eastern time on Thursdays. So make sure you mark your calendars, log in and join us. Scan the QR code in the corner so you have the schedule. Somebody specifically was asking about the integral of cosecant, cotangent, cotangent. And why is that equal to cosecant x, negative cosecant x, right? Well, the reason we often use this one is as simple as it's one of our derivative rules. If you remember going back to our derivative chapter, we learned the properties for the derivative of cosecant of x as being negative cosecant x cotangent x. So If I multiply both sides by -1, I get negative cosecant x is derivative is cosecant cotangent. Taking the integral, remember the fundamental theorem of calculus tells us that integration and derivatives are inverse operations, so they're going to go opposite directions. So if I start with this, the answer is going to be that if we're integrating. So that's kind of why the integral of cosecant cotangent is negative cosecant cotangent. So we really need to make sure for integration, we're really comfortable and familiar with those derivative formulas, because they are going to be what makes everything come together. All right. Ooh, related rates. I love related rates. Let's do a related rates problem. A lot of great questions coming in. I'm trying to get through as many of them as we can, but make sure you're putting those comments in the chat. Keep asking questions. And remember, we're here every Thursday at 4:15. Let's do a related rates problem. The most classic related rates problem is the funnel. That's got water in it, but the water is leaking out at the bottom. Let's give this thing some dimensions. Let's see, put my lids on so they don't die on me. Let's say this funnel is 5 feet tall. Let's say it has a radius, let's see, if that's 5, that's about 2. The water is going to be leaking out at, let's say, 2 cubic feet per minute. Out. So that means its change, its rate of change, that's the volume shrinking out. I'll even label it. That's the change in the volume with respect to time is going to be a negative because it's shrinking by that amount. And let's say we're interested specifically in how the height is changing. How fast the height is changing when the height is equal to let's say 4 feet. So we want to know how fast is the height changing. So we need a relationship that relates how fast the volume is changing to how fast the height is changing. That's the related rates. We want to know how these rates of change are related to each other. First, we need to establish kind of some formulas that connect these things to each other. So one thing I see is we're talking about the volume of a cone. The volume of a cone, you might have to look this one up, is 1/3 pi r squared times h. The problem with this equation is it's got volume changing, radius changing, and height changing. I only care about the height and volume changing. I don't care about the radius changing. So we're going to try and get rid of that variable. And the way we're going to get rid of that variable is we're going to draw a couple triangles in here. Notice this triangle has a length of 2 and a height of 5. That ratio 2/5 is going to be the same all the way down, which means when I have a radius and a height, as the water goes down, radius and height are going to be changing. So I can't use the number 4 because that's just one moment in time. This radius and height are changing as the water leaks out. The 2 and 5 were not changing. That's why I can use the numbers. But 2 is the radius, height is 5. And so we've got this equation that r/h equals 2/5. We want to get rid of r, so I'll multiply both sides by h. And 2h/5 is equal to r. So this r can be replaced with 2h/5. So same formula, but the radius is 2h/5 because of this relationship. We could go right to the calculus here, but a little bit of algebra is going to make the calculus much easier. So let's go ahead and simplify this. I'm going to go ahead and square this fraction. The way we square a fraction, we've got a pi on top, we've got an h on top. The way we square a fraction is we square the 2 to get 4. We square the h to get h squared, times h is h cubed. Over 3 times 5 squared is 25. And 3 times 25 is 75. So a little bit of simplifying there. So that on my next step, we're ready to actually take the derivative. The derivative of v with respect to time, that's what we know. We're going to plug that in just a minute. The derivative of h cubed, we drop the exponent by 1 and bring the exponent out front. 3 times 4 is 12, so we have 12 pi over 75. I could reduce if I wanted to, but we're going to use our calculator in a minute anyways. So let's keep that there. And then plugging in everything we know, the change in volume is -2 cubic feet per minute. Then we've got 12 pi times the height. And now we're talking about the height we're interested in. Ooh, did you notice my mistake? The derivative of the height. I didn't multiply by the derivative of height with respect to time. Chain rule. Derivative of h cubed is 3h squared times the derivative of h. Drop my eraser, 1 second. And we're back, okay. So now we're gonna plug in the height that we care about is 4 feet, divided by 75 times dh dt. We're asking what is the change in height with respect to time. We can do that by solving, by multiplying by the reciprocal of this. So we've got -2 times the reciprocal of this, which is 75 over 12 pi times 4 is equal to the change in height with respect to time. It's negative, which we would expect because the height should be shrinking if water is coming out. And I can just put this all in my calculator and it'll tell me exactly what that change in height is with respect to time. Related rates, a lot of parts to them, takes a lot of practice. The calculus part is usually pretty easy. We just take the derivative of both sides with respect to time in there. The catch is we want to make sure we get the right relationship, so the right variables are related to each other. A lot of those equations are going to come from geometry. So hopefully that helped answer your question. I see a couple questions about integration by parts. So let's do some integration by parts, and then we'll come back and do the integral of x cosine squared of x. Such great questions coming in. Thank you for those questions. I love it when you bring the questions, so we make sure that this office hour is your office hour. So keep those comments coming, those questions coming. We're going to answer as many of those questions as we can. Remember, we are here every week at 4:15 Pacific time, 7:15 Eastern time. If you want the official schedule, you can scan the QR code here. Let's do some integration by parts. Let's integrate x times the natural log of x dx. Let's make it a little more interesting. Let's go x cubed times the natural log of x dx. The idea of integration by parts is it's kind of like a reverse product rule. We've got to have some type of product in the integral, or at least something times dx, that we can split up into two pieces. One piece we can take the derivative of, and the other piece we can take the antiderivative of. The way I decide which piece, the x cubed or the ln x, which piece am I going to take the derivative of? I think about this acronym that says ILATE. And this is really just a guideline. It's not a hard and fast rule. So there are exceptions to it. But the idea is if there's any inverse trig, I want to make that my u. No inverse trig. Then I look for logs. Sure enough, I have a log. That's what's going to become my u for this problem. And then you look for any algebra trig or exponentials. But since we have a log going through the list first, u is going to be the natural log of x. dv then is going to be the rest of the problem, which is x cubed dx. So we can take the derivative of the natural log. It's 1 over x dx. We'll take the antiderivative of the x cubed, which is x fourth, times 1/4. Then we can use our formula for integration by parts. It is u times v minus the integral of v du. So u times v is going to be 1/4 x to the 4th natural log of x minus the integral of v du. We've got 1/4 x to the 4th. Divide out, and x leaves behind x cubed dx. And the goal of integration by parts is that this integral that we end up with will hopefully be easier to solve. Sure enough, in this case, it is. And so we'll go ahead and integrate it. We end up with, don't forget the 1/4 x cubed ln of x minus, increase the exponent by 1 to get 1/4, divide by the new exponent. So now there's an extra 4 down here. 4 times 4 is 16, plus c, and we get our solution by integration by parts. Go ahead and take a screenshot of that one if you would like it. And then we're going to go back to another comment that came in that was asking about a very specific integral that looks a lot trickier than it actually is. Let's see if we can break it down and make it easier. Last chance for a screenshot. I'll smile. Send it to me, I'll sign it. Okay, let's erase that. And the question came up, wanted to look at the integral of x cosine of x squared. The integral of x cosine of x squared dx. I'm assuming it's written this way. Let me know in a comment if I've got the squared in the wrong spot. Do you want the cosine squared? Because that's going to change things quite a bit. But I think this is what you want because this is set up for a very nice u substitution, where I can make u equal to everything inside the cosine, because that's going to make this into the cosine of u. That's a really easy antiderivative to take. Du, then, its derivative is 2x dx. There's a couple of ways to handle this. My favorite way is, let's try and make a 2x dx in the integral. I've got an x dx. I'm missing the 2. What's nice about integration by part, or u substitution, is with constants, don't do this with variables, that's bad, but with constants, I can multiply by any constant I want in there, as long as I multiply by its reciprocal outside of the integral. When I do that, we end up with 1/2 outside of the integral. The 2x dx, all is going to become du. What's left is the cosine of x squared, but the x squared is just u. And this integral, we know how to solve. The antiderivative of cosine is just the sine. But of course, we don't want to end up with a u. The problem had x's in it. So we're just going to substitute back into the original problem, knowing that u is x squared. So we end up with 1/2 sine of x squared plus c for our final solution of the integral of x cosine of x squared. Excellent. Hey, James Stark. Am I saying that right? Good to see you here. Even though you're not in math, you're loving it. Great. Excellent. Drew was asking earlier about why do we have to be greater than 0, epsilon greater than 0? The reason we're talking about epsilon and delta being greater than 0 when we're proving limits is because epsilon and delta are actually distances. We don't want to have a negative distance. That wouldn't make much sense. But we want a really small distance. So epsilon's greater than 0, but not much greater than 0. Excellent. A lot of comments asking for integration by parts and related rates. We already did that. Excellent delta limit proofs. Glad you enjoyed that. Jose Farina, I'm probably saying that wrong, sorry, wants to see evaluating indefinite integrals. Do you mean improper integrals, like with infinity? Because those can be fun. All the integrals we've solved so far have been indefinite integrals. That just means we don't have limits on them. And that's where you end up with the plus c. But let's do improper integrals, because those can be fun as well. Did I prepare one? No, I did not. We're going to have to make one up. Let's see how it goes. Let's do the integral of x e to the negative x dx from 0 to infinity. I hope that works. Let's see what happens. This one also solves by integration by parts, which is why I chose it, because there's been a lot of questions about integration by parts. So this is going to give us a chance to practice that integration by parts again. So let's let u equal the x, because remember I told you about I late. Exponentials come after the algebra of x. So that tells me the u is going to be the x, and the dv is e to the negative x dx. So du, the derivative of x is just dx. V, the antiderivative of e to the negative x, is negative e to the negative x. And we'll do that same formula. You often hear it called ultraviolet voodoo. That helps you remember it. Ultraviolet u times v, and then we're going to subtract the integral of v du. So u times v is negative x e to the negative x minus the integral of, there's another negative, which makes it a positive. Negative, negative makes a positive. E to the negative x dx, going from 0 to infinity still. When we integrate this, we're just going to end up with an e to the negative x. Because of the negative x, it's minus. And we're going to integrate this from 0 to infinity. The problem is we can't really do math with infinity. If you do math with infinity, weird things start to happen. We don't want that to happen to us. So instead of going to infinity, we're going to actually think about taking the limit as b goes to infinity of negative x e to the negative b minus, this should be a b too, minus e to the negative b. So we're just going to put b in there, randomly pick the letter b. We're just going to let that b go to infinity. We're going to take the limit as it goes to infinity. It might be easier to kind of visualize what's happening here if I can rewrite this as those negative exponents in the denominator. And to really see what's happening with this first fraction especially, if you plug infinity, we get infinity over infinity. We're going to have to L'Hopital that. So L'Hopital says we'll take the derivative of the top, which is -1, over the derivative of the bottom, which is e to the x. And now when I plug infinity into this, I get a huge denominator and a small numerator. That means this limit's going to go to 0. So we've got -0 minus, again, huge denominator gives us 0. Then we're going to plug in the bottom and subtract. When we subtract a negative, it becomes a plus. 0 divided by anything is 0. Subtract a negative becomes a plus. Plug in a 0 here. E to the 0 is 1. 1 divided by 1 is 1. And so a bunch of zeros plus 1 equals 1. And so it turns out the area underneath this function from 0 to infinity is exactly equal to 1. Pretty neat. That's how I would handle the improper integrals. Excellent. Still catching up on the questions. We've got a lot of great questions coming in. I know this isn't really calc. So what we should do a live with differential equations because we get a couple of those questions. Do a Calc 2 problem. This was a good Calc 2 problem. Calc 2 covers advanced integration methods, such as, you know what we could do? Let's do a partial fractions. We haven't done a partial fractions question yet. Let's take a look at doing one of those. It also looks at sequences in series, but I don't know if you're specifically asking about sequences in series. So feel free to ask about those if you want to see sequences in series. But let's do a partial fractions problem. That's kind of a classic Calc 2 problem. Let's do the integral dx over, let's see what happens when we do x minus 1 times x squared plus 1. That's not a simple partial fractions problem. So hopefully that can give us a fun little challenge. So the idea is we want to break this up into 2 fractions, one that has x minus 1 as a denominator, one that has x squared plus 1 as a denominator. But to do that, we need to figure out what our numerators are going to be. So we're going to let a be the numerator of x minus 1. And because this is an irreducible quadratic, it's going to be a bx plus c over that x squared plus 1. That's equal to the original fraction. And so when I multiply everything by the denominator, by this x minus 1, x squared plus 1, the x minus 1s will divide out, leaving just a times x squared plus 1. Then the bx plus c will have the x squared plus 1 divide out, leaving just the x minus 1. And that's going to all equal 1. There's a couple of ways we can solve for a, b, and c from here. One nice way is to multiply everything out, and then we're going to let the coefficients kind of guide us. So if I distribute the a, we get ax squared plus a. Distributing the bx, we get bx squared minus bx. Distributing the c, we get cx minus c is equal to 1. If I put these pieces together, in front of the x squareds, I end up with a plus b. And there's no x squared on this side, so we're looking at the x squareds. There's no x squared, so we're going to call that 0. Looking at the x's, we've got negative bx and plus c. So negative b plus c. There's no x's over here, so that's also equal to 0. Looking at the constants, we've got a minus c. And that's equal to a constant of 1. What's really cool here is if I add these together, a plus a is 2a. B minus B is 0, C minus C is 0, and that's all equal to 1, which means I know the A must be 1/2. Once I know that A is 1/2, A plus B is 0. So 1/2 plus negative 1/2 must equal 0. So B is negative 1/2. I also know that negative B, which makes it a positive 1/2, plus C equals 0, which means C must also be a negative 1/2. Because if I add B to both sides, you get B equals C. And I can check it in this other equation, A minus C, 1/2 minus negative 1/2 is a positive 1. So I know these values are correct. So let's plug them into this equation. So our original problem is actually equal to the integral of A, which is 1/2 over x minus 1, plus B, which is a negative 1/2 x, plus C, which is a negative 1/2 over x squared plus 1 dx. Let's factor 1/2 out of everything. I don't want to deal with the fractions. And then as I do that, we're going to also split this into two integrals so that we can handle the integrals separately. So I've got 1/2 times the integral of 1 over x minus 1 dx. That's nice. That's going to be easy. We're basically done with that part. Then I'm going to factor out a negative 1/2 out of the second one, which is going to give me x plus 1 over x squared plus 1 dx. Now, this would be really convenient to solve if this became 1 over u. That's the natural log of u. So if I make u x squared plus 1, du, its derivative is 2x dx. So to get the 2x, I'm going to multiply this by 2, which is going to give me 2x plus 2. And I'm also going to divide by 2, which makes that now a 4. Now, I only want 2x dx. So I'm going to take this x squared plus 1 and divide it by both terms separately, giving me a third integral that we're going to solve. So we're breaking this down even further, giving us 1/2 times the integral of 1 over x minus 1 dx, minus, don't forget this minus 1/4 is going to have to go all the way through, integral of, we'll put the 2x over the x squared plus 1 dx. Don't forget we've got another minus 1/4. Actually, let's pull the 2 out, which makes it minus 1/2. Integral of 1 over x squared plus 1 dx. All of that to give us something that we now can integrate step by step quite nicely. What color am I on? Red? This first one, that's just a natural log. So we have 1/2 natural log of x minus 1. The second one we purposely designed with the u substitution, so it would become 1 over u, which is the natural log of u. So this is going to be the natural log of the x squared plus 1. Minus, this last one turns out to be exactly tangent inverse. So we have 1/2 tangent inverse, or arctangent, of x plus a constant. And that is a beautiful Calc 2 type problem as requested. Go ahead and take a picture of it if you want. Save it, send it to me for an autograph. Just kidding. Hopefully that was helpful to you, though, in solving some partial fractions. I'm going to come back in and check in with the chat and see where we are at. So many great questions, actually. I'm going to go all the way to the top. A lot of great differential equations question. What if we have an irreducible polynomial to the third degree? Great follow-up to this question. So this was irreducible to the second degree. So I made the numerator bx plus c. If it's irreducible to the third degree, we kind of follow the same pattern. You drop one exponent and just count down. So if I had, just hypothetically, we're not going to solve this one because the algebra just takes a while and I want to answer as many questions as possible. But if I had dx over maybe an x plus 1 times x cubed minus 2x plus 3, for example. So there's an irreducible cubic. This does not factor. I don't think it does. Hopefully it doesn't. So with the x plus 1, we'd still have an a over the x plus 1 like normal. Then when I get to the irreducible cubic, we're going to start with 1 power less than this with the x squared and keep counting down. So we'll have a bx squared plus cx plus d, and just kind of keep counting down. So if there was an irreducible 5th power, we would do 4, 3, 2, 1 on the exponents to simplify from there. So great question. Excellent. We want to integrate sine to the 10th from pi over 2 to 0. Do you mean negative pi over 2 to 0? We normally put the, or maybe you mean 0 to pi over 2. That one might get ugly. Let's see what happens. Integral of, lost my place, sine to the 10th. From 0 to pi over 2. So I'm going to get this started to kind of establish the pattern I would use. There are formulas you can look up that'll help us reduce that exponent. But basically what I'm going to do is I'm going to reduce this down using the fact that I can rewrite this as sine squared x to the 5th power. And what's nice about sine squared is sine squared can be written as 1/2 minus 1/2 cosine of 2x. And that's still to the 5th power dx. And this innards are going to be a lot easier to solve. But the problem is that 5th power. So we're going to have to actually multiply this out to the 5th power and see what we end up with. And then we might have to use this property over and over again to split up. We probably will have several cosine squareds. We'll have to split those up. And it can get kind of involved. So, yeah, it's going to go pretty ugly from there. It's going to take quite a while. But that kind of gets you started on how I would solve that one. Blank on TikTok wants to see integration using a double U substitution. Let's see if we can do a double U substitution. And then maybe from there we can look at some sequences and series. I saw a question for that come in the chat as well. So a double U substitution, that's going to be tricky to make up, but let's see if I can do this. Let's do cosine of e to the 3x squared times these are tricky to make up. Hold on a second. I got to do a derivative. All right, I got a better idea. We're going to set this up by first doing a derivative of a chain rule that requires 2 steps, and then we'll integrate it to show that it gives us back to the original solution. And it saves me the work of having to make up the problem. So let's do the derivative of sine squared of e to the 4x. So the idea here is when we're taking the derivative, we're going to take the outsidemost function, which is the squared, and we're going to take its derivative, which pulls the 2 out front, 2 sine of e to the 4x. And then we multiply by the derivative of what's inside. The derivative of sine is cosine of e to the 4x. And then we multiply by the derivative of what's inside of that. The derivative of e to the 4x is 4 times e to the 4x, which is going to give us a total of 8. So one step at a time, we took the derivative of the squared, we took the derivative of the sine, we took the derivative of the e, we took the derivative of the 4, multiplied them together to get this. And what's nice is if I didn't know that was the original problem, I'm not going to erase it. Let's see if we end up back there. Let's say we wanted to integrate this. If you're really clever, you'll see a U substitution that makes it work in 1 step. I tell students not to worry about getting there in one step. You need to worry about getting there. So it's okay to do this for 2, 3, 4 steps. So one thing I notice is sine and cosine would work better if they had u's as inputs. If I take the integral, we have to say what we're integrating with respect to, dx. So I'm going to make u equal to e to the 4x. Du then, its derivative is 4e to the 4x. Well, that's not too bad because I can split up this 8 into 2 times 4. And we've got a 4e to the 4x dx. So now my problem is the integral of, we've got a 2, 4e to the 4x dx all becomes du. And we're left with the sine of u times the cosine of u. Now we can do another u substitution because we see the derivative of sine is cosine sitting right there in our problem. So let's not make u, we don't want to use u twice, so let's use a different variable. I like to use w because it's a double u substitution. See the little play on words there? That's kind of fun. Double u substitution is a double u. We're going to make w equal to the sine of u, which means dw is the cosine of u du. When we do that, we end up with a 2 times the sine, that's my w, times the cosine u du, all of that becomes dw. And now I've got an integral that we should be able to solve. We can increase the exponent by 1, divide by the new exponent's nice, it's just w squared plus a constant. And now I just have to work backwards to get to my solution. So w is the sine of u. So this is the sine squared of u plus c. But we don't want u, so we're going to keep going backwards. U is e to the 4x. So we've got the sine squared of e to the 4x plus c. And sure enough, that is the original problem that we started with, because u substitution really helps us do the chain rule backwards. So if you want to make up some problems to really practice this skill and get good at it for your test, make up a chain rule problem that has multiple parts to it, take the derivative, and whatever you get is going to be an integral that's going to require double u substitution, or triple if you made it big enough and complicated enough. Excellent. The integral of x minus sine x over x cubed. That one might not be solvable. That one makes me nervous to dive into that one. But I did see a question about sequences and series, and I think I promised a problem on sequences and series. So let's take a look at finding out if some sequences and series converge or diverge. That's the big question of sequences and series. Where's my sequences paper? Here it is. Let's say I've got the sum as n goes from 1 to infinity of the natural log of n divided by n. And the question that we want to do with this series is we want to see, does it converge to a specific number or does it diverge off to infinity? The reason we care is if this converges to a specific number, we can do some mathematics with it. If it diverges to infinity, things that diverge do weird things when we do math with it. So we want to make sure we're careful with that. So a lot of the times in Calc 2, especially, the question we're asking is not what does it equal. We don't really care what it equals. All I care is, does it converge or does it diverge? And so the way we're going to do that, there are probably about 6 or 7 tests that you can do to decide if it converges or diverges. One of them is called the integral test. So the integral test says that if I can take the integral from 1 to infinity, matching these limits, of the expression, if this equals a number, that means this integral converges, and it means the series converges. If this equals infinity, or if it diverges, if the integral diverges, the series also diverges. Now, something to be careful of is if it converges, it doesn't mean they both converge to the same thing. It just means that they both converge. So let's see if we can solve this integral. You might have noticed that we've got natural log and 1 over n. 1 over n is the derivative of natural log. If the derivative is sitting in the problem, that's probably going to be a u substitution problem. So we'll make u equal to the natural log of n, and du is equal to 1 over n dn. That's going to make the problem equal to the integral from, putting the limits into u, the natural log of 1 is 0. The natural log of infinity is still infinity, of u, and then the 1 over n dn all becomes du. And this is a really nice integral that we know how to solve. We'll increase the exponent by 1 and divide by the new exponent, and we'll integrate that from 0 to infinity. And you can see here as we look at this, when we plug in infinity, or at least the limit as it goes to infinity, because you never actually plug in infinity. When you plug in the infinity squared divided by 2 is going to be huge. This is ultimately going to diverge as an integral, which means this limit, this series, is also going to diverge. It's going to go off to infinity as well as you add up all of those infinite terms. Is it the hardest unit in Calc BC? I don't think it's going to be the hardest unit in Calc BC. Integration is probably going to be the most challenging unit because there's so many things to keep track of. The thing with series is it takes a lot of practice to kind of identify which type of series we're working with. For example, one thing I look for is, can I integrate this? If I can integrate, I know I can use the integral test, and then it solves really nicely. If I can't integrate it, another thing I look for example, is, are there factorials? Because if there are factorials, hello, Gianna, welcome to our live. If there are factorials in the expression, I'm probably going to use what's called the ratio test. So, for example, let's say I've got the sum of 1 over 2n factorial as n goes from 0 to infinity. And I want to know if this one converges or diverges. Well, as soon as I see the factorial in there, I'm thinking ratio test would be really nice. The idea of the ratio test is we have this Greek letter rho. It's kind of like a P, but it's like pushed on its side and squished a little bit. It's the Greek letter rho. We take the limit as n goes to infinity of the absolute value, but there's no negatives here, so the absolute value don't really matter in this problem, of the next term, which is 1 over 2 times n plus 1, the next term, factorial, divided by the current term, 1 over 2n factorial. We're going to simplify this. If the limit as n goes to infinity of the next term divided by the current term, that's the ratio test. If this ratio test ends up being bigger than 1, the whole series is going to diverge off to infinity. If this ratio test goes down to less than 1, the series is going to converge to some number. Now, if it equals 1, we know nothing. We're kind of at a dead end. So we don't want it to equal 1. We either want it to be bigger or smaller than 1. Leo on TikTok thinks this one's going to converge. Let's see if you're correct. We're going to take the limit as n goes to infinity, and we're going to multiply by the reciprocal of this, which will stick the 2n factorial in the numerator. And in the denominator, multiplying this out gives us 2n plus 2 factorial. And you can kind of see what's happening here right now, but just to make it really clear, factorials count down. So I could rewrite this as the limit as n goes to infinity of the 2n factorial over, we've got a 2n plus 2, and it's going to multiply by the next number below it, which is a 2n plus 1. And it's going to multiply by the next number below it, which is 2n, all the way down factorial. But I stopped there because it matches what's in the numerator, which means I'm going to be able to reduce it out, leaving just a 1 in the numerator. So I can see here as the n's get big, as the n's get huge, this denominator is going to just continue to be huge. And we have 1 divided by huge. And 1 divided by huge is just 0. Because 0 is less than 1, remember 1's our deciding factor, because 0 is less than 1, we're going to say this series converges. Excellent. There are so many great questions that come in. Number 2, if a series with 1 over n factorial doesn't converge, I don't know what it does. If it doesn't converge, it diverges. That's really the only option. Or we know nothing. If it equals 1, we really know nothing. All right. Well, we are quickly running out of time. I have had so much fun working through these calculus problems with you. And if you didn't get your question answered, don't worry, because we're going to be back next week at 4:15 p.m. Pacific time, 7:15 p.m. Eastern time to answer your questions. So come back with questions. Scan this code in the corner so you have the schedule so you don't miss any of our lives that we're doing this week. Also, Chegg is doing a special right now. If you put Chegg Live 50 in as you register for Chegg, you can get 50% off your first membership fee. So go on and check that out. Make sure you're following Chegg here on TikTok, YouTube, Instagram, Twitch for more learning content like this. Make sure you're also following me at Wallace STEM on all the same channels, TikTok, Instagram, Twitch, YouTube, and all of that. We are so excited that you have joined us. But until we see you next time, next week at 4:15 Pacific p.m. 4:15 p.m. Pacific time, 7:15 Eastern time, every Thursday. We'll see you next time. Thanks for logging.